you can imagine that it exists. It is some curve in this XY Z space. Similarly, I mean, and so on, that's how it goes. So that is the picture of dynamics which I want you to appreciate, that I can visualize the dynamics of a system as just a curve in some large dimensional space. If you give me 10 to the power 23 particles in a three-dimensional space, I'm afraid that I will need 6 times 10 to the power 23 axis, and in that space it will be a curve. But the point which I want to drive home is that it is a curve, and it cannot intersect itself unless you have a periodic solution. So that is the next thing, which picture, I mean, why these pictures are very important, that in this two-dimensional space, I tell you that I have a XY curve, and as time goes on, it goes like this. And if at some time it should happen that it intersects itself, then you are, I mean, forced to say that, look, you are going to be on a repeating trajectory. This is what it is going to be. So if there is an intersection of the orbit, then you go back to the start. I mean, you have to retrace that part of it, and what you have is a periodic situation. It can happen that in a three-dimensional situation, that you can intersect yourself, intersect and get back into a periodic orbit. But now life becomes more complicated. You need not intersect, but you can still be sort of regular. The answer can be in terms of two incommensurate frequencies, and then in this three-dimensional space, what you would be seeing is the system going along a torus. And so never comes back on itself, but never goes off too far either. It winds around on the surface of a torus, filling up the torus more and more as time goes on. So this is, I mean, while this is a solution which looks like A cos omega t, this is a solution which looks like A1 cos omega 1 t plus A2 cos omega 2 t, and omega 1 by omega 2 is not equal to a ratio of two integers. So then you have this whole thing. So what am I after? What am I after is that you increase the dimension of this space, and your trajectory has the capacity to become more and more complicated. So if the trajectory does not, in this two-dimensional space, if the trajectory does not close back onto itself, it has only one other thing. If it is not going to, I mean, that is, it can't it has to wander off at some time to infinity.
Sir, I have some question.
Yeah.
So the picture which you have shown, that A cos omega t, that part. So the A cos omega t part, which you have drawn, the dynamical system's y-x plane. So that part, after starting from that initial point, it is doing a closed trajectory at some point. Then we can't trace back the initial point from there. since it is in a loop.
I mean, look, this audio that I can hardly understand what you are saying, but do you let me try and address
Yes,
what I think. Just wait. You are asking that you are happy with the two-dimensional situation, that if it crosses itself, it has to go on repeating. You understand that, right? Do you understand that if this curve comes and crosses itself, it has to go on repeating that part of the orbit? Do you understand that?
Yes, sir. So I was asking a different question. I was asking that the car started from some initial condition at t0, and it happened to be crossing itself at some another point t1, and it forms a closed orbit.
Yeah.
But sir, from there, suppose a person happens to calculate the dynamical system at any point after t1, then it can't trace back itself to the point t0. Means it will be in a loop. It has lost its history already. Means the dynamical system can't evolve. Means it will evolve in a closed trajectory, but it can't tell us anything about the history. Means before t1, before forming the closed loop.
Right. Yeah, you are not interested. Yes, I get the point. Nobody, in all that we are going to talk about, nobody is interested in small times. You want to see that after a long time, where are you? It is only after, technically, it is that at t going to infinity, what do I have? So if it is dynamics which is periodic, then technically at t equal to infinity, I see it just going back, going round and round on a definite path, which is in this case, this path that I have drawn over here. But if you just increase one more dimension, and suppose your solution looks like this, and omega 1 over omega 2 is not a ratio of integers, so that, I mean, they are irrational numbers. Now you see they are going to wind round a tube over, like a cycle tube. The trajectories would live on the surface of a tube, but would never come and cross itself. If it were to cross, it would gradually, as time goes on, more and more, it will become dense on the surface of this tube over here, which is called technically a torus. So you, two torus to be more specific, because it is characterized by two frequencies. So on the surface of this torus, it just goes on, filling in every point on the, or at least trying to fill in every point on the surface of the Earth. So it is our interest, you are, yes, you are right, is only in what happens after a long, long time. Yeah. Good. So, so you see that as soon as I start increasing the numbers of variables that I have, x was trivial, x and y non-trivial, it gave allows me periodic solution, and then x, y, z, it can be periodic, but it can also have this particular feature. It can end up on the surface of a torus. So I put one, or every time, of course, you have the option that it can just go off to infinity. That, I mean, is bad luck. But if you are, or whatever, I mean, may not be so bad, it prevents, it stops all calculation at that point. But then if it is going to describe something which is meaningful, then it can't fly off to infinity, and the it remains bounded, and it remains bounded in some interesting fashion, either like this or like this. So that is if I have x, y, z. And the things become more and more complicated as things go on. So this is to give you a feel that dynamics is, it is important to visualize the dynamics. That is the point that I'm driving at, that calculating is not an option, at least at this stage. Even I wouldn't ask you to numerically investigate for yourself. It's a lot of work for nothing at this point. But visualize that what is going to, all my interest in is that I give an initial condition. So somewhere it is on the phase space, and what does the trajectory do? Does it loop back? Does it not loop back? If it does not loop back, how much of the space does it live on? And so on and so forth. So that is what is called a qualitative understanding of the dynamics. And if I'm going to talk about a large number of particles, then the only thing of importance is a qualitative understanding of the dynamics. So for our purpose, that is, so all right. I mean, this is so far as dynamics goes, that if dynamics is to be written as a set of first order equations, and all right, you follow the dynamics by looking at the so-called phase space. Phase space is, so we define the phase space, a space whose axes are x1, this is particle 1, x1, y1, z1, px1, py1, pz1, then all the way to x and y and zn, and px and py and pz. That is, I should have just asked, sorry. Should have kept it, sorry, didn't need this. No, do need it. Sorry, no, px1, no, need it. So px and py and pz.
Sir? So you earlier said, like, if the diagram in which we represent this dynamics, if it intersects to itself, then it should follow a periodic. Then there should be a periodic solution. So, like, aren't we avoiding a chance of the system getting out of this periodic state? Because when we are looking at the long time, at some point, if it gets out of this periodic, otherwise periodic state, then in the long
look, I mean, look, there is, if you are on a periodic state, you can't escape the periodic state. If that is your fate, to be on a periodic state, that's it. I mean, there is no question that today you are on a periodic state, tomorrow you will be somewhere else. If that is why I'm stressing the fact that all that I'm interested in is what happens at very large times. No question of transient behavior. That is the final behavior of the system. If it is periodic, it is periodic for the rest of the life of the universe. If it is quasi-periodic lying on a torus, it is so for the rest of the age to come. So that there is no question, no such word as I was periodic now and I am not periodic then. Does not exist in the lexicon. It is, if periodic at one time, it is periodic at all times. This is always for times which are sufficiently large. No transients in the system. All transient behavior has died down. T, I'm looking at it at sufficiently long time, and sufficiently long time means I have reached a final state, stable state. Actually, the word is a final stable state from which there is no escape. And the possible, as I said, the possible final state can look like periodic, it can look like this, and it can will have things which I can't draw, which look more and more.
If the potential suddenly changes or is time variant?
What?
So if the potential is time variant, then the momentum must change.
What potential change?
If the potential is time variant or changes abruptly.
These are no time dependence on the right hand side. No time dependence on the right hand side. If there is time dependence on the right hand side, everything is off. All statements are for situations which look like this. No time dependence on the right hand side. No, none. There, in that case, there is no such thing as orbits like this or this or this. It's a completely new situation. It can happen that you can still lock into something like this or something like, but that has to be fortuitous and only for some particular values of driving. So, yeah. Right. So no time dependence.
So the diagram in the A cos omega t part. Yeah, sir. If suppose the trajectory does not intersect itself, but it comes very much close to the curve, and it
that happens on this torus, no? It does not intersect itself ever, but it comes very close to itself. Yeah, I mean that is exactly what is happening over here. It does not close.
That's in 4D, means in a 4-dimensional space.
Pardon?
So the torus is in a 4-dimensional space.
See, the point is that on this torus, you don't close yourself because the omega 1 and omega 2 are irrationally related. For example, if omega 1 is 1, omega 2 is root 2. And you can plot it up and see that it will never close on itself. So the point is, no question of crossing. No question of crossing. Once you cross, you are back to periodic. So things can't cross. So I mean, actually, this is all the dynamics that I want you to picture. So, I mean, I'm willing to take questions now because this is, I mean, I have said everything that I have to say, namely that the dynamics that happens with a large number of particles is they may go off to infinity. We are not at all interested in that. So they have to remain in our sight. And if they remain on our sight, then that dynamics cannot intersect itself, and it can sort of fill out a certain part of the space. For example, in this two-dimensional space, it fills out, this periodic orbit fills out a curve. In this three-dimensional space, this orbit torus, it fills out the surface of this torus, which is a lower dimension than 3. So this is what is called a 2 torus. So in this three-dimensional XYZ situation, it fills out the surface of this 2 torus over here, and over here the period. And so you can now just visualize that as you increase the number of dimensions, they live on some kind of a surface which I mean, which you can't calculate, neither probably can visualize, but they live over there. The trajectories, just as in a on this torus, you can imagine that if it is a 10-dimensional or 18-dimensional situation, let's say the 80, there is probably some 16-dimensional torus on which this is, they are going around forever. So, and it takes an infinitely long time to visit every point of the torus. So, but yeah. So that is the picture of the dynamics of this conservative system. It's a therefore, I mean, it's a conservative system. It has a conservation law, which is the energy conservation. And there cannot, so there is no time dependence anywhere. So that conservation laws, if I allow for time dependence in parameters over here, nothing that I have said so far can hold. It's a completely new game and much more complicated. But I'm talking about specifically a system which looks like this, and generalization of it to a large number of particles, but always have a conservation law. The energy, which is p square over 2m plus phi of r, is a constant as the dynamics goes along. And because it is a constant, you are restricted to a smaller subset and not, you don't fill the whole space. Get the point, right? I mean, because if I have a constant, then in this xp plane, it will be a curve which is a lower dimension than this two-dimensional space that we are talking about. So one constant is always there in this conservative system. The constraint is that E equal to p square over 2m plus phi is a constant of motion. So this is a constant of motion This room becomes unbelievably hot. I mean, what the this place is, I don't understand. Do they run a heater instead of a cooler?
Sir,
Yeah.
so I just wanted to clarify. In that particle that goes with a cos omega t, I'm just asking. So we don't call something periodic if it goes out of this periodic state after a particular time. I mean, after maybe t seconds in this periodic character, it goes out of this periodic state into another path. Then we don't call it periodic. Is that what you meant? And if we have to call it periodic, it has to perpetually continue in this state forever.
Now, let me, how can it get out of the, how can a cos omega t ever get out of the periodic
No,
state?
sir, not with a cos omega t. If we have a potential that defines predeterminacy.
Look, if the potential is not time dependent, nothing can happen. No? I mean, I have taken, let's say, a potential which is half kx square. And so the solution is x equal to a cos omega t with your omega as square root of that. And done. I mean, you can't go out of it. I mean, there will be, I mean, in over here, it is so trivial that, I mean, right from t equal to 0, you would be tracing out this ellipse over here in the xp plane. I can make the right-hand side a little more complicated so that you may not immediately, by making the potential a little more complex, but you may not immediately pick up the periodic orbit, but once you do, you are sunk, because the point is that here you are, as soon as you have come over here, intersected yourself, your loop is done and you can't do anything after that. That's the whole point of the periodic orbit, that in this XY plane, I draw this orbit, it starts going around, and over here, when it is a one-dimensional oscillator, it just doesn't, I mean, must have seen Lissajous figures or things like that, at least. I mean, 1 year has gone by. So these figures over here, which are Lissajous figures, which is essentially what I'm talking about. So in these A cos omega t drawn on this XY plane, so X is equal to this, Y is equal to minus omega A sine omega t, giving you these Lissajous figures over here. But if I make things a little more complicated, where things are, I mean, the phi has been made, I choose it according to some fancy of mine, and then it is, maybe it starts out and does not immediately recognize the period, but once it does, which is that in its course of wandering, it comes back over here, then there you are. That is, once you are on it, you can't leave it. That's the point. You see, so long as there is no dissipation, no pumping, no question of parameters changing with time, you are stuck on this orbit. Yeah. It seems to me that only a couple of you are asking for clarification. What about, I mean, the rest of you, have you got the picture? I mean, this is unfortunately not a classroom.
Yes,
Yeah,
Yes, sir.
you got, all right. I mean, if you have not, I'm not saying that this is something simple and immediately. It is complicated, the picture is difficult, but if you have any please write to me, I'll try to clarify, because this not being a classroom, it's very difficult. I can't see you, I can't understand whether you have, seeing makes a big difference. Then I can figure out whether it's making sense or not. But in this, the audio, when you ask questions, I have to imagine what the question is and so on. It's a mess. Yeah, go ahead.
Sir, with that A cos omega t problem, before it gets into periodicity, it's actually exhibiting non-periodic character. So we have not included that in the potential. So how do we explain that?
As I said, if it is, I can put you on a potential where there are possibly 2 or 3 possible orbits which are closed. For example, I can give you a potential which is minus x square over 2 plus x square x4 over 4. Now, there are possibilities that you can be, this is a double well, you can be oscillating in one well, or you can be oscillating in the other well, or you can, so that will depend on what initial condition I give you. So I give you an initial condition, and now the system, as it evolves, will have to figure out which of the 3 is it going to take. So then it is not so trivial anymore. It wastes a couple of steps to figure out, and then once it figures out which is what the initial condition that I have given, which orbit does it belong to, then the solution then of course is not x equal to, if I give you x dot is equal to y and y dot equal to minus x, life is actually absolute. That is when the solution is x equal to a cos omega t. And this is a situation where, I mean, you start out x, y anywhere over here, it immediately gives you a plot like this. But if I were to give you something more complicated on this side, in particular, a condition where y dot is equal to omega square x minus lambda x cubed, which allows for various possible orbits, which would be chosen actually by the initial condition. And now when I put you on a initial condition, it will take this is an exaggerated picture, but the numerics will take a couple of steps before it actually gets into the orbit which it wants. So that's. So, all right. So till now, I'm happy that given this system, whatever system you give me, I can give you, in principle, give you a solution if it looks like xi dot is fi depending upon the whole set xj. So if this is the situation and there is a conservation law which is essentially summation, let's say xi square or whatever, it may not, this power need not be a square, it can be a, but some, all right, let me just put it like this, some g of the set xi equal to constant. So if I, there is a conservation law which is this, then trajectories will live on, will be bounded, will be some complicated trajectory, but they will, if there are n, I goes from 1 to n, then
Yes, sir. Yes, sir. Now we can hear you.
Can you please repeat from that I equal to 1 to n?
So we can't hear you.
Right? Can you hear me now?
Yes, sir.
Yeah, the battery had died, so
Yes, sir.
that was the point. Anyway, so all right, back on track.
So can you please
Yeah.
repeat from that I equal to 1? From I equal to 1 to n. From that part you were inaudible.
Oh, yeah, sure. Yeah. The system that I'm talking about, look, I mean, I talked about xi dot equal to pi over m and pi dot equal to some function which is a function of x1, x2 to xn. So this I goes from 1 to. So that is what Newton's law looks like. We agreed when, I mean, the potential, this is the potential is in, sorry, this is the potential, and so it's xi double dot is derivative is some function, which is the force. So look, that this can be, if I change the notation, if I, all right, will probably help you. If I call this y and if I call this y, then these two, if I define a y which is the set of x and the set of p's, so that over here I have x1 to xn and I have p1 to pn, then I can call this y over here goes from y1 to n, and y1 to yn means x1 to xn, yn plus 1 to y2n means p1 to pn. And in terms of that, these two equations can be written in that notation as just one equation, which is yi dot equal to some function of I as these yj's, which means that for the first n, I have these, and then when y goes from n plus 1 to 2n, I have these. So that's just a notation. Yeah, sorry, I mean, that should have explained, but that it is just a notational change. Yeah, got it? So this, I mean, should have been a y. Sorry, I had a and then yeah. That's what this means. It's just a question of. So all right. So the point is that at this, if you have come this far, at this point you should be feeling happy, in the sense that, look, I mean, I know what the dynamics is all about, and then we can get on with the rest of the course. Point is not done. Let me now tell you what the next tricky point, which is actually going to be the basic. This is just the formal aspect of the mechanics, but now comes a qualitative part of the mechanics, which is vital to what we are going to do very soon, almost immediately after it. But you have to, this is something, pay very good attention to what is going on. So my task is, I have to talk about dynamics of a n-particle system. My contention is that this is a hopeless situation, that there is no point in trying to talk about the dynamics of a n-particle system, if n is very large. So now I'm going to explain why. I have explained to you that formally, if I have an n-particle system, I can write down Newton's law for it, and in principle, I can integrate and give you the solution. Now, I'm not saying that is wrong. What I'm going to tell you, that the solution means nothing. So that is the next part of it. You know how to get the solution, but now you are going to be told that out of that solution, you get no information. So that is the next big step in this course. So, all right. So I'm going to make life as simple as possible for myself. I'm going to take the n particles to be on a plane, and the plane is the plane of this blackboard. And I'm going to put them on to make them nice and easy, I'm going to put them on a lattice. So I have imagined that this board is a sort of table, a horizontal table, and I'm going to play. I've arranged these particles over here, and maybe I want to play billiard on that table. That would certainly make life tough, and that would be something quite actually beyond solving. But therefore, the billiard that I will play would say all these are fixed balls. So all these red and blue and this are all pinned to the table, and only one is free. So all these except for this, all of these billiard balls are glued to the table. I'm going to, let's say there is some hole over here, and I have calculated very clearly in my mind that if my stick is going to hit this one over here, then this is going to go and hit that chap, and maybe place it somewhere else. So this goes and hits this chap, reflects off, then this reflects off over here, and here is some pocket, and this is going to go and do that. So I have done, it is just elastic collisions, so it simply reflects. So it reflects, which means that here is this fixed disk over here. Here is the normal, and the other chap comes, and this center of mass has a velocity in this direction and comes and strikes over here. And it will be, the dynamics is going to be a reflection, and so if this is theta, it's going to be. And then if it comes and hits another its drawings are a bit complicated. I want the normal to go like this. So the center is over here and here. And then the trajectory coming like this, going like this, going to go like this. So that's what I have planned on. That these are fixed things over here. I'm going to take aim, strike it over there. This comes here, strike, and then goes off like this, and off it goes. And in that case, I'm happy. There is a pocket over here. This will go and fall in the pocket. The spacing, the radius of a disk, these are two-dimensional, so they are not really balls, they are disks. So disk is 3 centimeter. Distance, this spacing over here, spacing between disks, which is essentially center of the disks, is, let's say, 20 centimeter. This contraption, that is the stable and with disks, is placed in a room at one end of a room, which, so this thing, this table is over here in a room which has the scales are sort of, I mean, the width of the room, let's say, is 5 meters. And what happens is that when I'm taking aim and making sure that all this will go according to my plan, a man weighing 80 kgs, let's say, all these numbers are prefixed to, they are not unrealistic numbers, but they are obviously pre-assigned numbers so that the final result comes out right. So, I mean, that is the numbers, and the numbers are important. So, I mean, it's something which, so this man suddenly comes, and question is, would his presence have any effect on the dynamics? So if it was a question of whether, now comes what do I mean by the dynamics? If it is a question of I shoot this off and ask the question that will it reflect from here? Sure it will. Will it reflect and go and hit this as I had planned? Sure it will. But there will be some error, right? Because I did not take the existence of the man into account. So there is going to be some error. And you are going to say, what error? I mean, 80 kg man standing over here, the gravitational constant is nothing. So what? We are talking about this man affecting this small mass over here to the point that all my planning over here would go to waste. Well, that is what I want to calculate and show what is going to happen. So this is the setup, that you have all these disks static except one on which you have taken careful aim, and it's going to, after a set of collisions, go and fall into a pocket which is lying somewhere over here, and you have planned out your strategy, which is entirely possible, and you have done a correct calculation. But as you take aim, this man appears and, well, just wants to watch you in action. And question is, what is going to happen? Nothing should. But is that true? So, all right. So what will happen is, first thing, there is going to be, this disk is on its way. You have given it a hit, it's on its way, and this man has come. So there is, let's say, the moment you hit, this chap appears, the trajectory that you had planned. So here is the static disk. Here is the moving disk, and the velocity of the center of mass is such that it would go and strike over there and go away. So that's what your plan was. And how well will it be honored? So this man is going to give a push delta x. I have to give you another information. The time, that is, I need to give you the velocity with which I'm going to strike this disk. So I'm going to the time between, so instead of specifying the velocity with time between two collisions, I'll give you that is 1 second. So I want to know that your trajectory is going to get deflected by a certain amount delta x because of this gravitational force. So what is delta x going to be? I'm not going to use any equalities. It would all be almost.
Excuse me, sir, someone got disconnected. Could you please let him in?
What happened? What happened?
So someone got disconnected. Could you please let him in?
Does not give the option here, I'm afraid. Let's see. There is a waiting room, but there is no joining option. What's going on? All right. Let's see, got it. Should be in. Yeah, changed. Right. All right. So I need to find out what the deflection delta x is from the trajectory over here. So what's the force? The force is GMM over L square. L is this 5 meters. The acceleration, this is the Newtonian gravity, m times acceleration, which is a. So the acceleration over here, so that cancels. So this is that. And delta x is going to be half and gm over L square times t square. So that would be the amount of deflection that you are going to have. So that deflection, and this is, one has to calculate it. So, and that is important. So it is half. Half is not important, but anyway, we'll keep it. So G is, I'm going to use CGS. That's what I grew up with and can't really leave it. So 6.7 into 10 to the power minus CGS for capital G. 80 kgs is 80 into 10 to the power 3 in CGS. 5 meters was what I said. So that is 500 centimeters. So it is 25 into 10 to the power 4. and then there is 1, which is this t square. So this is equal to, therefore, your delta x is roughly, so there is 6.7 times, so this is 10 to the power minus 8. Here is 10, so this becomes 4. So roughly, I mean, this is 6.7 is like 7, 7, and then you have 8, and I have 2, and this is 10 to the power 4. This is 10 to the power minus 4 from here, and minus 8 from here, 10 to the power minus 8, and it is to be divided by 25. So there is 25 over here. So this is like 56. 56 by 25 is like 2. So this cancels the 2. So this is 50, this is 56. So it is 10 to the power minus 8 centimeters. So as expected, nothing. So delta x, so this man walks in, the deflection of the particle as it goes and hits the other is going to be 1 angstrom. And I can live with that. And so you say, rubbish, you don't need to worry, you are not going to miss. All right, very good. So I have a error of delta x over here. Now, what does error of, now, so there is going to be, so you expect this trajectory, so let's, but this is not the end of the story. I have to here is the static disk, and I expected that, my expectation was that it would come and hit over here. No deflection, it would come and hit over there. But there has been a deflection which is very small, so it does not hit over here, but hits over here. So this distance, is delta x. So that is the delta x that I have drawn. So now I'm exaggerating things in drawing this. The delta x has turned out to be 10 to the power minus 8 centimeters. So I'm not really worried. But the delta x, now there is a delta x change over here, which means that there is an angular, you were not expecting the angular change that is going to happen. You were expecting it to come and hit at some angle delta theta over here and go off at some angle theta and go off at some angle theta. But now, because there is a shift delta x, your theta, which you were banking on, has got a shift, which is delta theta is equal to delta x divided by the radius of the. So that's once again, nothing to worry about. That delta theta, delta x was 10 to the power minus 8 centimeter, r, which is 3 centimeters. So delta theta is a minuscule angle. So you are not worried over here anymore. But look at this quantity. It is delta x by L times L by R. So what has happened is that you see delta x by L, when you were talking about, so far as this strike went, you were talking about angular deviation which was delta x over L. So it was in the course of this length L, which is the distance between these static disks. So that was the angular deflection, and that has blown up by now when it is the second time around, that is, you have the second, the first reflection of this, there is a blowing up of the by a ratio L over R. If you were not to have that collision over there, then you would say that the angular deflection that has happened from this route is delta x over L, and that n. But there is a collision over there which brings in this change, which the delta theta, when it's now on its way, is delta x over R, and therefore has become modified by this factor which is L over R. Now you come and hit the second, and now you come and hit the second static chap, and you go off, and it is again the same story, that there is going to be a deflection which is going to come over here exactly as it happened over here, and the factor which relative to this is again going to be L over R. The factor relative to this for this strike was L over R. Initial error in traversing this distance L, and then magnified because now it is this radius and it is a L over R. So next time around, it is going to be delta x over L into L over R into L over R. And now after n collisions, so after n collisions, n collisions, initial error delta x over L, angular error, is blown up by the factor L over R to the power n. The initial thing over here was delta x, which is 10 to the power minus 8 centimeters, divided by L, which was, as said, 20 centimeters. So it was like 10 to the power minus 7 divided by 2, right? So initially it was like 10 to the power minus 7 and 2. This ratio is 20 divided by 3 to the power n. So this is like 7 to the power n. So here is 10 to the power minus 7, maybe call it 10 to the power minus 8. (10 to the power minus 8) into, which is like 7 to the power n. So let me just go 7. So this goes, this factor over here, 7 to 49 to 343 to 120,373 21 24. So 2401 to 7 again. So this is now 20. So it's like 160,000 7 again, and now it is 112,000 0, 0, 0. So it is 1.12 times 10 to the power 5, 7 again. And now it is 10 to the power. The next step takes you to 10 to the power 6. And you can see the thing. It is 1, 2, 3, 4, 5, 6. And here is the 7th step. Go 2 more, 10 steps. 10 steps and everything is gone. You are not going to, you have no idea about what the dynamics is going to be. So 10 steps, all that it takes, n equal to 10, and the dynamics does not go as you wanted it to go. What is going on? That a small, I mean, it would have, had this man not come around, it would have gone on perfectly. But this man comes around, provides infinitesimal perturbation, and now it does not take you an infinite number of steps to feel that perturbation. You feel the effect of that perturbation after just 10 steps. And that is the law of large numbers and small perturbations, and makes all predictability go down the drain. So here is a trivial example. This was popularized by somebody in Oxford a few years ago, in a kinetic theory course. Absolutely superb demonstration, really, that look, the whole business of saying that this is the way the billiard balls are going to behave is susceptible to a small effect like a man walking through the door. And this is what is so complicated about a system, about the dynamics of a system of particles as opposed to the dynamics of a single particle or two particles. So one particle system or two particle systems like the sun and the earth, or even the planetary system because spread out over a huge distance, small perturbations can die out over here, over there. But small perturbations in this real life situations can, if there are a large number of particles involved, be absolutely killing. So this is the point that one is after. And why is it so important for us? It is so important for us because it means that when I'm going to talk about when I'm going to take a box and talk about 10 to the power 23 particles flying around, there is no point in trying to say that Newton's laws will tell you the answer. I mean, it will tell you the answer formally. Sure, I mean, you can, in principle, write down 10 to the power 23 first order equations and get answers. But that's useless because any small change in your initial condition, you'll have to provide an initial condition for finding that solution. And if you change your initial condition ever so slightly, you are going to get a completely different answer. So this is the kind of dynamics which is essentially unpredictable in spite of the fact that the dynamics is determined by Newton's law. There is nothing very deep going on over here. I mean, it is not that the laws of physics are being changed or anything. It is just that you have to realize your handicap when you are talking about a system with a large number of particles. So when I'm talking about a system with large number of particles, it is virtually impossible for me in practice to talk about the individual position or velocity of each individual, of the position and velocity of each individual particle. That is an impossibility. And therefore you say that, look, this is not going to work for me. I'm going to take a probabilistic point of view. I will not ask myself the question that if a particle, I won't ask this question if particles are at the points x1, x2 up to xn with momenta p1, p2 to pn. I will not ask the question that what if particles are at this position with this momentum, what will the dynamics be? I will not ask that question, although I know that that is the dynamics which is being followed. I know that they are following Newton's laws and would be moving around according to what we have been saying for the last couple of hours, yesterday and today, taken together, that although it is correct, it is of no use to me, because any small change in the initial, who knows what is the initial condition for these 10 to the power 23 particles. And I have just shown you that if I have a small change in initial initial conditions for 10 particles, it's a lost case. So therefore, you just reset your thinking process and say that, look, I'm going to be happy with talking about the probability of a molecule being at a position X and having a momentum P. So I reduce my expectations and just say that I want to know what is the probability of a molecule being at a particular position and having a particular momentum. Now, being at a particular position, what should be the simplest thing? That the molecule can be anywhere. Nobody is putting a constraint on it. The collisions are going to spread them all over the place. So the obvious thing is to say equal probability of being anywhere inside the box. So that's not so if I have these particles moving around inside the box, each particle has equal probability of being anywhere in the box. But velocity is a different thing. It is not, it is obvious that no particle can be flying around with a very high, that is, a large number of particles will not be flying around with very high energy. That requires a lot of energy to be given to the system. Neither would there be, I mean, if I look at distribution of the magnitude of the velocities, neither would there be a very large number of particles just sitting at, say, almost at rest. Most of them would be moving around with some average velocity, but with a distribution. And that is the whole subject of kinetic theory, that you give up, for very good reason, the attempt at getting a description of these. And what is our purpose? To talk about a system with 10 to the power 23 particles. So how would Newton want me to go about it? Newton would say, write down the equations of motion and describe what is going to happen to these particles as time goes on. What we have just seen, that while that is technically the thing to do, that is also going to be an impossible thing to do, because it would all mean that any solution that I get for that system may be a correct solution, but you change conditions ever so slightly, it will not be the right solution. The solution would go away very far. And therefore, the only thing that I can settle for is a description in terms of probability, and that probability, so far as the position goes, the particles can be anywhere with equal probability, and so far as the velocity goes, the probability cannot be high for high velocities, neither can it be very high for very low velocities. That is something which we want, which we need to calculate. So this is the basis for this course. I mean, you are entering a completely different way, a new world, where you are giving up on Newton and saying that I will not be talking about the coordinates and momenta. I will be talking about what is the probability of the particle having a velocity between 10 centimeters per second and 10.00001 centimeter per second. So that is the probability that that probability is what I am interested in, and out of that probability, predictive power has to emerge. Get the point? I mean, this is, look, I mean, this is not exam material, so don't get worried about the fact that which always, I mean, one has in the student days, that one is being told something which you will be examined on. I'm not mad, I wouldn't do this. But the point is, you need to understand why and why one is doing what one is doing. There is a reason behind leaving Newton and taking up a different kind of description. All right? So, and the reason lies in Newton's laws itself, that if you worry about Newton's law for a large number of particles, you find that it is absolutely a hornet's nest. You can't find your way through it. And that is the problem which Maxwell and Boltzmann realized in their own ways, sets up a very different description. And it is the Maxwell-Boltzmann view of dynamics which gives rise to the essentially properties of gases, which we would be focusing on for almost all of this course. So this is the background material. It is worth understanding, and therefore, I mean, the point today, I guess I have to stop. Yeah. So it is time for me to stop, but you think about this. When we meet on Monday, you can, I mean, seek, because now we are going to be on a, after this, once I have assumed the probabilistic description is the best, thereafter it is down to standard statements and calculations. But what happened over the last 2 lectures is what sets the basis for what we are going to do for the next few weeks. All right? Yeah. Yeah.
So the case which you have explained now is the billiards ball. It is just few number of particles, but this type of similar situation happens in the atmosphere modeling also. Climate change.
What?
Atmosphere.
Atmosphere. Yeah. What about it?
Means does they also follow the probabilistic method to calculate the?
Yes, they do, because there is a gravitational. See, unlike the particles moving around in this room over here, where it is possible for all particles to explore every point in this room without a difficulty. If I'm talking about the atmosphere, there is gravity, and more particles would be at a lower altitude than at a higher altitude. So that means that things have to be over here. For particles in this, molecules in this room, I'm going to say that all space points are equivalent. For particles in the atmosphere, to which will come maybe a couple of weeks, I don't know, maybe not probably next week, but the week after, then I would have to say that, look, there is a gravitational potential energy which I have to worry about. Yeah. Right. All right. I mean, think about it, and if you, whatever queries, will obviously handle it, and then we'll go on to something calculating the pressure. See, the bottom line, PV equal to NKT. This course has to explain to you why I have PV equal to NKT. And when does it fail? That also, but that's a minor issue. The important issue is, why do I have PV equal to NKT? That is the point of the course. And this is the background material for trying to understand why did one arrive at, over the 17th and 18th and 19th century, to PV equal to NKT. Good.